Let's distinguish between fluids and liquids. When I say fluid, I'm including both gases and liquids, all right? So the air in the room is a fluid. If I suck the air out of this can, it crumpled. It's like I sucked it and pulled it in. So in terms of gauge pressure, that's one way to think about it. If you ignore the fact there's pressure outside, that's why we often think that way with a straw. Say, oh yeah, if I use a straw, I'm sucking the fluid up the straw. But really what you're doing is you're removing the pressure that's pushing down on the fluid inside the straw. You're removing that in the same way that this pump removed air from inside the can. And the thing that's actually doing the work, right, is the air in the room pushing on the outside of the can. So you're right. If the pressure over here, we can think of that as pushing to the right. And so I would draw it this way, and I'd say that force, let's label it by its magnitude, it's going to be the pressure on the left times the area. What's the area of that thing? Oh yeah, it's L squared. Right? So that's the force due to the pressure on the left side of this thing. Does everybody agree with that? Same thing for the right. Pressure on the right, the fluid on the right side of the box, or right side of this volume, results in a force going the other way. Make myself a lot of room, but there we go. Pressure on the right times L squared. And also, in and out of the board is true too. So I could draw a little dot coming at us and say, oh yeah, that's pressure maybe in the back times L squared. And then there's this X, which means into the board, and say, oh yeah, there's a force there. That's pressure in the front times L squared. Right? And then there's pressure on the bottom that's pointing up. Pressure on the bottom times L squared. And let's see, there's also pressure on the top times L squared. So we've got all 6 of our forces. But there's another force acting on this thing. What's that? Gravity, and that points straight down. So I need another force that goes down like this, and that's mass times g. Okay, great. So now if we use Newton's second law in the x direction, let's say, we discover, well, first of all, this is a hydrostatic equilibrium. So what's the acceleration of this thing in the x direction? 0. So if you write Newton's second law in the x direction, right, what we get is that pressure on the right times L squared has to, let's see, is that positive edge negative, and then you get plus pressure on the left, L squared equals ma in the x direction. Oh yeah, but that's 0. So that just means the pressure on the left equals the pressure on the right because the L squared cancel, right? Pressure on the left equals pressure on the right, as it had to. So in other words, the pressure only depends on the height. It doesn't depend on your horizontal location, right? And that makes sense. But here we just did it. We just proved it using Newton's second law and doing it all formally. But we know that from the argument I made before about perpetual motion machines and stuff like that. Same idea. But there's a way to formally show that if you want to prove it to a degree that you know what you're talking about. And then what about the vertical direction? Well, this is more interesting, right? Because in the vertical direction, you're going to say, well, it's not that much more interesting. But anyway, to me, it's more interesting because now we have 3 forces. We're still in hydrostatic equilibrium. So even though there's gravity acting down, this little piece of water inside the tub, it's not moving. It's not accelerating, right? So that means that pressure on the bottom times L squared, is that pointing up? Yeah, it's pointing up. Minus pressure on the top times L squared, right? That's this force. Oh yeah, and also minus mg, right? That has to equal may, but that's 0, hydrostatic equilibrium. But now the pressures are no longer equal, right? And which one's bigger? Pressure on the top or pressure on the bottom? Who thinks top? Who thinks bottom? Yeah, so the bottom's half and it's correct. Pressure on the bottom, that's the case with the vote went the right way. Although people do vote both ways. It's easy to get it backwards when you're not careful. And the book actually has a formula that I always read backwards because it says pressure equals P naught plus rho g h. And by h, they mean height. They mean the height from where you are to the surface of the liquid. And that's a little confusing. I prefer to write it the other way. So don't get confused about differences. And just make sure you know what conventions are when you're doing it. So my convention is, well, first of all, the physics is that, as most of you correctly just stated, or responded, the pressure on the bottom is greater than the pressure on the top because these both get the minus sign, right? Gravity's pointing down, and so is the force to the pressure on the top. So these together have to equal this, and that means that pressure on the bottom is bigger. If you want to relate all this, though, let's figure out how to express m in terms of the variables in the problem. Well, we want to get rid of these L squareds out here. How can we relate m to L squared? Well, we've got a formula for density, right? Mass is density times volume. And in this problem, what is the volume of the little fluid element? L to the 3rd power. So that means I can rewrite this, right, as volume of my little piece of my little fluid element times rho times g. Oh, and I can rewrite that then as L to the 3rd rho times g, right? So now I can plug all this stuff in. What do I find? I find that the pressure on the bottom equals the pressure on the top plus rho g, and then it would be L in this case, right? Where L is the height difference between the top and the bottom of the fluid element. And in general, I would write it this way. I would say pressure on the bottom equals pressure on the top plus rho g h. So this is different than the book's convention. The book uses h to mean, like, the deeper you are, the bigger h gets. I'm using h here to mean height, as the name suggests, right? So the higher up you go, the bigger h is. So by that I mean, yeah, I mean height. Height of the thing, of the, yeah, well, let's see. Let's do it this way. Pressure where you are equals some reference pressure plus rho g h. That's the way to say it. So that's the height relative to your location. So both these equations are true, and I think they both, to me, they're the more intuitive way to write it. But this is height with respect to where this was measured, right? So in other words, if you want to know what the pressure at the bottom is, right? Let's see. Did I say this right way? Yeah, because what is h relative to the top? So this is measured. If we substitute in here and say, what's the pressure at the bottom? Well, pressure at the top is what I'm calling P naught. Then what is h going to be equal to in this problem? Yeah, it would be L. Let's make sure I got my sign right. Pressure at the bottom. Oh, am I putting you on? Let me make sure I got my convention the right way around. Well, maybe I'll play it safe. I'll say that the top thing is exactly right. Pressure is, oh no, it's bugging me. It's backwards. I mean, this is the formula I want to write that way. So now I'm happy. The book has it the other way with the positive sign. Yeah, see, the book's messing me up still. I blame the book, even though it was my mistake. But there it is. That's the correct formula if I'm going to use it with this convention. And the book uses the plus there, yes, again, because they mean height to mean below the reference point. All right. Whatever convention you're going to use, stick with it. The top thing is the easiest for me to keep straight because it's explicit about bottom top, and the thing on the right is a positive quantity. But both those equations are true. Okay, good. So now, how can we check this? We can explicitly measure this with this device right here, fancy device. What I'm going to do is I'm going to measure the pressure exerted at the bottom of this cylinder of metal by lowering it into a tank of water. And here I'll turn this on so you can see what the number says. So it should say 0.74. Can you all read that? Yeah? Is it on? Oh, it says 2.74. Interesting. I'm getting a different number over here, but no matter. I think it's adding. Something on. Actually, it's on the right channel. Oh, Very interesting. All right, the 0.7 force is the same. Okay, it's going to be different numbers back here, but as long as it does the right thing. Let's see if it does the right thing. Well, as I raise and lower this, and what is this measuring? This is a force meter for the top of the string. So it's measuring the tension in the string. You want me to think about it. It's how much force it has to exert to the string as an accelerate, and the string is actually exerting the equal opposite force on the hook as the hook exerts on the string. So by Newton's third law, right? So if I lower this thing into the water, what will happen? Well, let's first just lower it and see. And the way I'm going to do it, I'm actually not going to lower the mass. I'm going to raise the water. Doesn't matter, but that's what I'm physically doing. So if I raise the water up, well, nothing happens. And at some point, it's just going to touch the water. So now I'm just right at the water. Ah, just touched it. All right. So now there is some water just beneath, and in fact touching the bottom of the mass. But did the number change at all? Not really. It didn't change for me. I'm glad it didn't change for you. Somebody for yesterday had 1 over 3.3. Anyway, so what does that tell us? Well, what should the pressure be just beneath the surface of the water? Well, this right here, these two formulae, right, tell us how to relate pressures in different heights inside of the water. But we still have to figure out what our reference pressure is going to be at the top surface of the water, right? So let's think about Newton's second law again. If we consider a very, very skinny, very, very thin fluid element right at the surface of the water, and go just above and go just below and ask what will the difference in pressure be? Well, as we saw with this problem, the difference between the pressure above and the pressure below is proportional to the mass, right? It's proportional to the weight, right, of the water that's between the two. If it's really, really thin, it goes to zero. If that height goes to zero, it goes to zero. So it turns out that the pressure above equals the pressure just below the surface of the water. So we've already said the pressure in the room is 1 atmosphere. Again, is that absolute or gauge pressure? Absolute. So let's do this in absolute pressure just to be consistent. We'll say, all right, so outside the surface, just above the surface of the water, right, we've got, here we go, and here's my surface of my water. We've got pressure equals 1 atmosphere. That means that if we go just below, actually let's draw this without so much perspective so you can really see exactly where I'm pointing. So here's my tank, right? Here's the surface of the water. So right above and right below. Well, the pressure is also 1 atmosphere. And this is, of course, in absolute pressure. Okay? Absolute pressure. So it hasn't changed. And that's what we just measured. We lowered this thing. Because after all, if we did Newton's second law acting on this piece of metal, we'd say, well, there's an upward force due to tension. There's a downward force due to mg, where m is the mass of the piece of aluminum, right? And then there's an upward force due to the pressure beneath times the area of this thing. And we're finding that you say, well, wait a minute, the pressure below is 1 atmosphere. How come when I just touch the water, why don't I see a huge force now of 1 atmosphere times this area? What other force is acting on this thing? Well, what about the air above this? What's the pressure on the air just above the cylinder? 1 atmosphere. So there's two opposing forces, just like there is in that fluid element we drew up there. On the top, there's an atmosphere times the area of this thing, of the cylinder, pushing down. Same thing at the bottom. It's just on the bottom has to be water, on the top has to be air. So those are balancing each other out. In other words, there's no buoyant force right now. There's no net force due to these various pressures of fluids near the surface of the object. It all balances out to zero. There's no buoyant force right now. There's just mg pointing down, and in fact, the tension in the rope is just equal to mg. It's the same as it was before touching the water. Now, if we submerge this further, what we'll start seeing is that the bottom part of the metal now, right, is going to be in contact with water that's got a bigger pressure as it goes deeper in the pool of water. So should the tension go up or down as I lower it, as I immerse this piece of metal deeper into the water? Tension should go down because there's an upward, that's right, there's an upward buoyant force that's opposing the force of gravity that goes down on this thing. So and I'll say this, and students will get this wrong on the final, I guarantee it, but you won't. And the statement is that buoyant forces always point up, right? Force of gravity always points down, right? But the buoyant force always points up for the same reason that the gravity force always points down. So that's a really useful thing to remember, so you don't get confused with your conventions in your science and stuff. And you can see it's easy to get confused. I mean, floundering a minute ago with that equation, trying to figure out which way. We got it right in the end, but buoyant forces always point up. I always remember that. Okay, great. So let's submerge this guy further and see what happens. So I submerge him, and sure enough, at least for the number I'm seeing is going down. Let's see if yours is going down. Looks like it is. It's down to 60. So it was 2.7 something, and now it's 2.6 something. So sure enough, the tension is being decreased, right? It's decreasing. Being decreased. It's decreasing. This is not your English class, I know. So as I keep doing that, it continues to decrease. And what am I doing? I'm submerging more and more, a bigger volume of this piece of metal deeper and deeper into the water. See that? And now I've got it so it's just at the surface. The top surface of the metal is right at the top surface of the water, right? And we haven't gone to zero. It isn't that there's zero tension anymore. If this thing were balsa wood, right, and I did this, at some point, what would happen? It'd float, right? I mean, this is a piece of metal. It's got bigger density, greater density than water, right? That's why metal sinks, right? But balsa wood floats, and the reason it floats is it has a smaller density, right? Just like cream has smaller density than milk, so it floats on the surface. And in fact, before we got this far, the tension would have gone to zero. The buoyant force would exactly canceled out with the force of gravity before it's fully submerged, right? So we wouldn't have gotten this far. The string would have gone slack, and the balsa would be floating around, and, right? So now what happens if I continue to submerge the piece of metal? Well, the bottom of the piece of metal is going to be going deeper and deeper, right, in the water, and that means it's going to experience a greater and greater force, just as it has so far. But is the tension going to go up or down, or stay the same as I submerge it further? Now, I heard it stay the same from somebody. Who thinks it's going to go up? Who thinks it goes down? Who thinks it stays the same? Yeah, lots of people are not voting on that one, and I think the majority of you those who voted, they got it right. But people voted for all three categories. So let's submerge further and see. So your number right now is 248, and mine's 0.48, so it's only the most significant digit that's off. I don't know what's anyway. All right, 0.48. Okay, so now let's see. Let's go to the meniscus here over the top. Okay, so now it's fully submerged. Now if I keep submerging it deeper and deeper, well, it's not changing. And why is that? Because did it change? What? What's funny? Oh, it's now 0.8. Yesterday I would have thought, somebody's up there, Anyway, all right. So, okay. So so it hasn't been changing. And in fact, if I measured this thing with a reliable device, right, that actually gave numbers that didn't change willy-nilly, we'd find that the tension's not changing as I go deeper. Why is that? Well, the pressure on the bottom is increasing as I go deeper. But what about the pressure on the top? Pressure on the top is also increasing by the same amount, by rho gh, where h is that distance compared to where it was when it was in the air. And down here, it changed by the same amount, right? So, in other words, once an object is fully submerged, it doesn't matter how far below the surface of the water it is. It experiences a buoyant force that is only a function of its volume. It doesn't matter how far below the surface it is. Now, if it's only partially submerged, it's more subtle, right? Because then you can have different buoyant forces, anywhere between the maximum possible buoyant force and zero. But you can think of it also in terms of volume. You can say it's just the buoyant force that an object would experience that had the volume of the submerged volume of your object. So if I only have it half submerged, right? If I only have it halfway in the water, then it experiences the same buoyant force as an object that's half the size, that's fully submerged, that is half the size of my original object, right? So if I had a cylinder that's only half as tall but the same cross-sectional area, for example, half the volume, right, then the buoyant force it experiences when it's fully submerged, same as the buoyant force this guy's experiencing. So let's think that through. We're gonna revisit this in a few minutes and thinking of it another way. But I keep talking about the buoyant force and its volume. So let me just tell you a fact, and I think we're gonna yeah, well, we'll revisit this in a minute. The fact is that the buoyant force, when you make a free body diagram for some object, right, it has a buoyant force that is equal to its volume times the density of the fluid it's submerged in, right, times g, and it's always pointing upward. So you'll say, okay, well, I've got mg on the object, and I've got some upward force, and I'm going to call it F sub b, buoyant force, right? It's always pointing up, and the buoyant force turns out to be equal to, well, you can either think of it as the pressure below, well, let's see. If you have a nicely shaped object, right, like a cylinder, easy to calculate, you know what the top area is and what the bottom area is, and the sides are vertical, right? They're not flat, it's not a box, but they're always vertical, so gravity is always pointing in a direction that's, well, so the pressure on one side equals pressure on the other side, they cancel out, right? The only pressures that can actually contribute to the buoyant force are going to be the pressure on the very top and the pressure on the very bottom. So it's a very simple object to think about. Well, in that case, you'd say, oh yeah, the buoyant force is just going to be the area, the cross-sectional area of the thing times the pressure on the bottom minus the pressure on the top. Remember, this is a bigger number than that is. This is a positive quantity, right? Times the height of the object. So I'm just sticking this in from the formula we had before, right? Let's call this the height of the object. Well, I'll call it L, height of the object, right? So I've got some object like this. L, this is the area A, times G. And that's just, oh yeah, I need something else, do I? Do I need something else? See, that's pressure, that's a force per area. Multiply that, I get a force times the distance. Oh, I don't need G. Yeah, that's right. So this is it. That's the buoyant force. Well, this thing turns out to be the same, right, as the volume of the submerged part of the object times rho times G. And what rho do I want? It's very important. This is the rho of the fluid. So that's the density of the fluid, not the density of the object. In other words, when you calculate PD and PT, right? Well, there they are. What is this difference right here? It's just equal to rho G times oh, well, I'm thinking too hard. I saw things over here that are buried in there. The area times the difference in the pressure. Okay, so let's just write it out. It's going to be equal to rho GH. Yeah, well, that's it. It's rho GH times the area. All right, well, what is H times the area? That's the volume. Now, I apologize. A couple times now I've gotten myself balled up, but it's a very simple final formula, and it's a very simple idea. It's just the density times G times H. Well, what is that? That's the volume, so it's rho GV, right? What is that? Well, this, G, what is rho times V? So rho of the fluid, right here, and this is the submerged volume. Well, rho times V, density times volume, is just mass. That's the mass of the displaced water, in this case, or fluid in general. Could be an oil, right? Could be the oil in that case. So in other words, the buoyant force is just the mass of the displaced fluid, or displaced water, right, in this case, times G. In other words, it's just like mg. Just a gravity force. Oh, you can see it past the bell jar here. It's just mg. But what m? It's the mass of the displaced fluid. So in other words, if all you know is what the volume of your object is, or how much of it, actually, if you know what the submerged volume is, right, and you know what the density of your fluid is, you can immediately calculate the buoyant force. Okay? It's just the volume, the submerged volume, times the density of your fluid, times G, and it's pointing straight up. So that means if I'm standing on the bottom of the pool, so I'm denser than water, right? So if I'm not holding my breath too much, and there's no flotation device right around me, if I blow all the air out of my lungs and I hold still, and I sink to the bottom of the pool, I stand there, I still have to exert, there's still some force on the ground, some normal force to keep you from going into the bottom of the pool. I'm still denser than the water is. But I don't feel as much pressure on the bottom of the pool as I do right now, right? Like when I'm standing here in air, right, I feel some force from the ground. If I'm underwater in a pool, I feel less force. And when we calculate, so this way of calculating the buoyant force works. I can say, what's my volume, right? And how do I calculate my volume? How do I measure it? What's the easiest way to measure my volume? It's not an integral, I'll tell you that. It's some crazy function. So Archimedes, right? Archimedes was faced with this task in a way. The king said to him, look, I want you to come up with a non-destructive test, non-destructive, right? I don't want you to destroy my crown. I'll cut your head off and destroy my crown. So a non-destructive test to test whether or not my crown, which was made by some guy, I provided the gold, and then he gave me that crown, right? Some jeweler made the crown for him. And he wants to make sure that the crown is completely full of gold and nothing else, no lead mixed in, right? Because obviously, if you give somebody much gold, you ought to make me a crown. The crown is back, it looks like gold on the outside, but maybe there's some lead inside. So the first thing the king did was he weighed the crown. Or he did it himself, and he hired somebody. So he has one of his people weigh the crown, said, oh, it weighs the same amount as the gold I gave before. Right? So this is the test he did. He said, okay, I've got a scale, I've got tension over here, these are equal, oh yeah, that's L. That's L. What's the torque? Right, here's my pivot point. And here's my crown. Okay, hanging over here. Here's my block of gold over here. And it's the same amount of gold I gave him before, the artisan who gave me this thing back. And sure enough, the torque here, the torque from this same as the torque on this moment arm, or I should call it on this lever right here. So he's got some bar. This is the center of the bar, right? Define the positive direction for rotation. He did everything right. And he said, okay, so is this a positive torque over here or a negative torque due to the weight of the crown down here? Due to this tension. Is it a positive or a negative torque given that about the center of mass right here? Positive, because the crown's pulling down, right? The tension pulls down right here. And over here you get a negative torque, and they're equal and opposite. So that tells him, okay, as long as L equals L, this thing has equally distributed mass, then that means that these things have equal mass right here, right? But that's not good enough, because he could have taken out, 3 grams of gold and added 3 grams of lead. That's not a good enough test to check that. All that checks is whether he took off some mass and didn't add anything else to replace it. So Archimedes was tasked with this, and he didn't know how to do it first. Like, how could I check that the gold, without drilling a hole in it, non-destructive, drill a hole in it, head chop down. So he goes home, and he had one of his people draw a bath for him, right? And he gets in the bath, and he was the courtier, like he hung out with King a lot, ate very well.